So actually, so we want to talk this pumps and turbines actually. So pumps and turbines are most important part in a process pipelines. So those have some purpose. Ones to pump, deliver the energy to the fluid, and finally a fluid moves to a distance, maybe upside, maybe horizontal side, maybe any side. Turbine, turbines are being used to extract the energy from the fluid and just to convert in some other forms, so just like in music. Turbines mostly are used for power generation actually. Uh, so what we have, these were some videos which I will share to you on the YouTube actually. So these shows that how the workings of pumps, cavitations and timings and all this. So I will explain all of this to you actually. So what we have pump and pumping system, this is what you have. You actually provide the energy balances in the pump. So before whatever entering the before the pump, you have some energy of the fluid. And once you added a pump, you are imparting some energy. So this is energy delivered by the pump actually, this one, this particular component, H pump. So it is the energy delivered by pump in per unit weight of the fluid actually. The quantity of this is actually per unit weight of the fluid. So dimension of this is meters actually. Now, this right hand side, as we have already done some calculations of the pump there. So this is total energy on the another side of the pump. And this HL capital is total head losses incurred in that entire pipeline between zero point 0.1 to zero point 0.2. HL include your major loss, HF, major friction, the mean the losses only because of the straight pipe length, and H minor is only because of all fittings. Fittings we have already known that fittings you need just to control the flow. You need a valve, or sometimes you change the directions. Sometimes you make the connections. So these are various sort of fittings. So you have nipple, elbow, flange, coupling, union, socket, and walls actually. All are comes in the fitting. So this is the general expression for that. So these calculations we already did in previous class actually. So what the pump do actually? So if you have a reservoir here, so you are connecting a pump and it is the discharging a fluid. So let's say in this particular position here. So in this case, what you have here, that pump is below this particular tank. So this particular fluid will always fill this particular pump entirely. And what will happen that in this case, the fluid in the pipeline would be available up to the level of the fluid inside the tank. Fine, this level actually. Now, in this case means this much actually static pressure is always available at the pump. Fine. So that pressure divided by rho g is called static suction head. So that is always available for this particular pump actually. Now, once you will turn on the pump, so pump will suck the fluid from this particular pipeline. So once you turn on the impeller thing, it creates some sort of the lower pressure, and lower pressure will suck the fluid from backside, and then it deliver to the another side because you are imparting energy by the help of the motor. So whatever that mechanical energy you are providing with the help of the pump impeller, that is being transmitted to your fluid, and finally you are the raising its pressure further to lift it to a further height. So just like this is here. So this was the initial the level of the fluid. Now you are the discharging to this level here. So this is your the discharge head actually, discharge static head. This much you are is being delivered by your pump. Okay. So this is from your HL actually, H pump actually. This much is being the delivered by the pump. Uh, now, if you suppose here you have the means another configuration is this one. that now you have lifted the pump up, because most of the time is this previous configuration is possible to us when our tank is above the pump, means when we construct the something. So this is one of the configuration happens in case of industry also, our household also, your sometime in your, because we can store the fluid in some particular tank and we transmit it from there. That is the one configuration. So in this particular time, fluid is always present inside the pump. So there is no problem. You can turn on the pump anytime. It will always suck the fluid actually. Fine. Now see this particular end thing. By chance, let's say your pump is providing some energy, let's say 2 kilowatt. So that 2 kilowatt is let's say 100% of that 2 kilowatt is being transmitted to your fluid. Fine. Hello.
Yes, sir.
Yes, sir.
Now that 2 kilowatt, and now that is the mean the energy. Now you want to divide the term that Q and rho and G. How much flow rate you want to take? Based on that, you can calculate the head delivered, because the energy of the pump, the delivered by the pump is QH rho G. Fine, fine. So H is the head of the pump, means how much height is being transmitted by the pump only. So in that case, I can write that particular term here actually, so that you can understand well. So in this, what you have here, so this is power of the pump. So that you can take a different symbol for time being. Not available. So power would be your flow rate multiplied by your density multiplied by G and QH rho G actually. Okay. So this is where Q is just a flow rate. Fine. Now you want to calculate the H of the pump. This is H pump actually. This is the height delivered or by the pump something. If you can write it in this another format here, so you can write this head of the pump and how much height would be given by the pump would be your power delivered, how much power you are giving to the pump, this much, and divided by the term here, this actually that this one. So here, this is what your height, how much height or how much length it can transfer. This is from here, Q, rho, and G. So this is in terms of height only in terms of height. Now what you have here, flow rate. By chance your flow rate is too much high, so this value would become, HP would become your low, correct or not?
Yes, sir.
So, so in this case, you cannot say that you can fit any pump in any particular size of actually of your pipeline. So if you have bigger diameter pipe, your pumps, the smaller pump of lower capacity cannot give you any discharge. It cannot come. I mean, by chance, uh, let's say your flow rate is fixed. You can calculate height of the pump from there. Let's say you have 1 meter cube with the flow rate. You know the power, let's say 2 kilowatt. You know the density, you know the G. So you have calculated a theoretical maximum discharge of the pump. By chance, this line, yeah, the static line, this tank is more than that. It means you are turning the pump on, nothing would come out. Your discharge, the point is too much high, as which cannot the delivered by your pump, but you are giving energy to the pump continuously, and you are saying nothing is coming out. Okay, we can run it more time, more time. Over the period of time, nothing is getting discharged outside. Entire fluid is there in that pipe only. And due to that, your temperature of that fluid will get heated up. Over the time, will convert it to the vapor. Your finally your pump will burn out. So those things are need to be taken care all the time. That what should be the head delivered by the pump. My discharge point should be either equal to that or slightly less than that to serve the purpose well. Did you get the point?
Yes, sir.
So that is one thing and each pump can give you a particular height. So after that, we have to put the another pump and another pump. That is called a series combinations of pump. Means that you can put one pump here and the means the another pump after this line here. So you are putting a pump one after another in the series combinations when you want to transport the fluid to a higher height or higher distance, because each pump can travel up to some distance only. Fine. So this is called the series combinations of the pump. In that case, you cannot change the flow rate. Whatever flow rate is given by the first pump, same flow rate can be transferred by the pump 2, pump 3, because the mean that nothing is coming in between. So this is called series combinations of the pump. Another combination is parallel. By chance, let's say you want more flow rate to go upside, but your height is fixed. You want to deliver the fluid, let's say 10-meter height. So you can put it, your height is fixed. So you can take any pump. Now you want to have more quantity of the fluid. So in that case, you have to put several pumps in parallel connections. At this particular point, you have to put here pump 1, maybe pump 2, pump 3, so that your discharge can be increased. Okay. So in parallel connections, you are actually mean the increasing your discharge of the fluid. In the series combinations, you are increasing the your head total head delivered to the fluid. Now let's see here. So this is one combination. Another combination is this, that your pump is slightly up. This happens in all case of that whenever your water level or fluid level are stored in a underground water or underground tank. You see in large the localities these days, you have a tank inside the basement all the time. So, but they have the freedom there because the basement is not too deep, so they can fit a pump only at the basement only. So that is the combination all the time. This one in real life, in domestic means the applications we have this one. But whenever the level we are the sucking the fluid from a ground levels and all this is the condition. Here the liquid level is always a very lower than the pump. Now, this is what your pump is, that you should have a capacity of your pump. It should be able to suck the fluid at least from this much depth. Just like you are, the straw thing, you are the sucking actually your cold drink with the help of the straw, and you are the sucking with the help of mouth. So in the mouth, you are somehow creating a vacuum. You are the sucking up, right? You are decreasing a pressure in the mouth so that your fluid can be lifted up. Correct or not?
Yes, sir.
So by such that straw level is too much large, you will not be able to suck the fluid because your mouth has some capacity to create the suction. Yes or no? So same thing happens in case of pump. Each pump can suck the fluid at some particular gap only. Beyond that, they will not work. So this is the called the suction, the lift of the pump. And this can be calculated first the theoretically part also. How do we calculate the theoretical suction lift? After that, we have to design that the location of pump would be either equal to that or slightly lesser than that to make the safer side. Fine. So this is the condition which always fix that where should I fit the pump above the liquid, the level actually. Correct? And in this case, this is your total static head because your fluid is finally going from the bottom of this tank to this top discharge point in this. So this is the total static head in this particular case. Discharge head is this because from there the fluid is getting discharged from pump to a discharge point. Now let's see how to calculate all these particular points here. So you have the means two combinations. One is this combination where pump is lower than the fluid height. Another combination when pump is above than actually height of the fluid here. So in this case, you have the static suction lift. In this case, you have here static suction head. So head is a positive quantity, lift is a negative quantity. We have to lift it up the something by means of vacuum here. So this is how you are calculating. Now this is the means the another way that you want to that this is the energy line something. So at the energy line we are not going to talk much about here. Now before that actually this is what I told you here, efficiency of pump. So what you have here, this is the discharge capacity and head of the pump. Each pump has some power. Fine. So is that power, and power is being calculated Q P equal to QH rho G. H is the head of the pump. So this is the plot is being plotted in that way. The capacity, that how much capacity you want to withdraw. Based on that, you can have a available head. How much head would be delivered? You are multiplying by the efficiency also here. So if you are not discharging anything out, so in that case, you will have a maximum value of head. Here you say the full head here. After that, as you will increase the capacity more and more flow rate you want to take, your head is going to decrease because finally you have a product. Your product or power of the pump is QH rho G. So if Q is more, your head will automatically will get down. Fine? Hello?
Yes, sir.
Yes, sir.
Now after that, what will the happen beyond a particular point, if you are taking more and more amount of Q, up to some point, your the efficiency of the pump will increase more means you are able to transport the fluid. Means if you will increase the diameter more and more, you are taking more and more fluid out. What will happen over the period of time, after some particular time, let's say you have reached to this particular value, you have reached to a maximum thing, this is the maximum fluid. If you will increase the further the diameter of the means your outlet, after that you will not able to discharge the fluid. We will say that nothing is coming out from the pump. So your pump is working fine, but only thing you have diameter has increased, it too much, discharge has become too much high. So the no energy, no head can be provided by the fluid. Fluid would be inside the pipe only itself. So after that, you have the efficiency of the pump. Efficiency means how much mechanical energy we are providing to the pump and how much it is the delivering. So the delivered energy to the fluid divided by the actual energy, that is called the efficiency. Fine. So after a particular value of Q, this efficiency will keep on decreasing. It will reach to the highest value here. After that, it will keep on falling. And then your pump will burn out. So that's called failure actually. So in between of that, wherever they cut actually at this particular point here, this is the point here. So this is called here the best operating point where head and efficiency curve intersect each other. Okay. Now this is the point here. This is the maximum possible point. This is the break-even point here. This is the maximum possible flow rate can be discharged by a particular pump. So this is the maximum thing. But here your head delivered is lower than this particular point. Because the height is here, let's say here, 60 only. And the efficiency has become the 60%. Your head is also low. But here flow rate, the maximum discharge can be given by the pump only. So this is called the break-even point. You should not operate your thing beyond this particular point. This is the corresponding flow rate. This is the maximum rated capacity of the pump. Okay.
Okay, sir.
And operating thing, the safe operating point is this, where the headline and efficiency curve intersect each other. These are called the pump performance curve. So from here you can calculate this is the efficiency, maximum working efficiency. You can read a corresponding point. So this practically come nearly 70% or the 77 something, 60 to 70% something. Okay. Now these are the different pumps actually. How would you select the pump actually? So this is a total head and this is the gallons and the capacity. And now you have a discharge diameter of the pump here area. And based on that, you can actually choose your which diameter pump can be chosen here. Now, this again, this is the thing actually I was talking in the previous curve here. Here you had here the capacity. Now here is the impeller, the diameter. Diameter 1, diameter 2, diameter 1, diameter 3. So as you will have more and more the diameter, you are decreasing your head. Head is the mean the lowering down. You see here, D3 diameter is more compared to D1, and if the diameter is less than D1, let's say your head has increased. So you have to means optimize the two. Okay. This is what we have talked already here. So you have the head and the means the efficiency. This is the flow rate, and where your head curve and efficiency curve intersect the each other. This is called your operating point. And you see here, which I was talking to you. Generally, efficiency of the pump in the operating point is 66 point. You cannot increase more than that actually, as per existing criteria also. And this is the point here. This is called a break-even point here, because after this, the efficiency of your pump decreases. So you are not supposed to operate in any case beyond this, because after that your pump will burn out. You can operate in between of this range. Your head would be lower, but your efficiency of the pump is decreasing, because beyond this particular point, your efficiency is continuously decreasing here. This value will come here. So head delivered of the pump is low all the time. So you can, in this case, you have to always take care of this particular point. So this is the another graph of the same type. Now, this is what I was talking here, the multiple pumps to you. So this is what you have, two pumps combinations here. So this is what pump A, this is actually your pump B. Now what will happen here, one pump combinations and two pump combinations. So if you have, let's say one pump can discharge the fluid up to, let's say 10-meter height. After that, this is here, pump 1 and pump 2. So this is the series combinations. So in the series combination, you are increasing the head delivered to the pump. So first pump can give the head up to this particular point. You have added one more after that. So this will increase the head to double actually. Okay. So in case of the series combinations, your head delivered by the pump would be added actually. You can keep on adding more and more. In case of parallel, you have this parallel combinations. In parallel combination, because each pump have a different head. By chance, you have a pump of same make, same model, same capacity. So head delivered by both the pump would be same. Let's say this is the same here. Head delivered by both the pumps are same. Only thing your flow rate would be added actually. Your flow rate would be added because then by chance you have same capacity, then that the flow rate would become Q1 plus Q2. So wherever you want more of discharge, more mass to be transported, you have to use a parallel combination. Wherever you want to have more of the discharge head or transportation point, you have to add the series combination. Fine. Hello?
Yes, sir.
Now you have various type of pump, a centrifugal pump, and then you have a positive displacement pump, the reciprocating pump, rotary pump here. So these are the pump check valves and all this. Uh, res- so this is what the centrifugal pump is. So here this is the, you have a, let's say front view, this is the side views of a pump. Whenever you will open the pump, you will see this type of actually figure inside that. So this one here is called impeller actually. This is the impeller, and this is the impeller eye. This particular hole is impeller eye. Here the fluid is inserted to the pump, and this impeller moves in this side only. This moves in anti-clockwise, not in clockwise directions. And then the fluid, whatever is inside the inserted at the impeller eye, will thrown out to the outside of the casing due to your centrifugal force, and then it will move this side, and finally this side is bigger, and fluid lift up of this particular side. So wherever your side of the diameter would become bigger, your velocity would become lower, your pressure head will become higher only as per the Bernoulli concept. Okay. So this way the fluid work, and this cavity particular thing is called volute actually, volute chamber, and this is the impeller here. So impeller, this is the most commonly used the impeller actually, and now this is again this is a fixed combi. Here you have everything is fixed. Once you have a pump need to be connected with the help of the motor here. So you have the motor here. In between of you have a stepping box, a shaft, a gland, a seal also there, and so to make the proper connections of the pipe. So this is actually, and from here the discharge will come. Inlet is already would be inserted at the impact of that. Now this is what you have here. This is the impeller we were the talking here. So you see here, these are some eroded marks, right? Can you see that? That here, this is not the smooth one. Hello?
Yes, sir.
So this is being eroded over the period of time. So what does it happen here? Whenever this pump impeller moves to a high the speed, you have a very low pressure at the impeller eyes because their velocity is high. So what will happen is that in case of pressure becomes lower than the vapor pressure of your main fluid which is being pumped, some amount of that being converted into the vapor. Once it is converted to the vapor, it moves to a high pressure zone, and then that vapor collapse. So vapor collapse means you have a vacuum inside, and then a nearby fluid runs at faster rate to that. That's like a impact of jet something, and finally hit this metal surface, and that the hitting of that's called pitting actually, and that over the period of time it eroded all the surface of the impeller. Finally it get damaged, so that's called due to a cavitation phenomena a pipe. Wherever it will move at a high speed, a low pressure would become lower than the vapor pressure of the flowing fluid, and it converted to the vapor actually. And once that vapor bubbles are formed, those collapse over the period of time where they move to a high pressure zone, and that pitting is called the erosion. That's just like a hammering of the impeller actually. So that is called a cavitation part here. This is something some means design of let's say the capacity that how we will end at that particular slide because you might have the another class. So positive displacement pump, these are some their criteria that piston pump can give you the pressure up to 50 atmosphere, plunger pump up to 150 atmosphere, diaphragm pump actually up to that 100 atmosphere, and efficiency for generally that let's say a small pump is 40 to 50% and 70 to 90% for the large pump actually. So we will talk all of these, and I will share you all those videos, and everything is there in that, so that you can get some idea how does it work actually. So I will show this actually this that how does it work and all this. Okay, so the next class we will talk about that. So I would say that you just watch those videos which I will share to you today, and so that you for you it would be easy that what this pump at, how does it work and all this. Okay,
Okay, sir.
so we will end this class here actually.
Thank you, sir.
Yeah.